Hello, I'm a presenter of Team6 이승준. Our team members are 이재우, 강민서, 서시현, 이승준, and 정성일. Let's start the presentation. Before starting our presentation, let me remind you of our last week presentation briefly. Last week, we found out why Skydeck was used in absolute world and introduced other construction methods associated with Skydeck. And then we explained how they were applied to absolute world towers. The three main construction methods were Skydeck, RCS foam, and EFCO. Skydeck and RCS foam allows absolute world towers to accurately implement different angles of slabs rotating on each layer, and EFCO climbing elevator formwork system speeds up the turnaround time of absolute world towers core. This week, I would like to explain the vibration control system that skyscrapers must consider. Two things the engineer had to consider to design the skyscraper absolute world towers were earthquakes and wind. Before explaining each one, you should first be aware of the resonance phenomenon. There are the natural frequency of the building and the frequency caused by the external load. When a force wave having equal frequency with the building is applied from the outside, intensity of force wave is increasing as the amplitude increases and is called resonance phenomenon. Resonance increases the risk of a building collapsing. Let's find out the effects of earthquakes and wind on absolute world. First, the impact of an earthquake. Since the natural period of the building is calculated by multiplying 0.02 to building height, the natural period of the absolute world is proven to be 3.59 seconds. However, the vibration period of the earthquake is 0.5 to 2 seconds. Thus, the risk of building collapse due to resonance caused by earthquake is not high. How about the wind load? To determine the effects of wind load, you need to know the mechanism through which the wind passes. As the wind passes through the building, a vortex flow is created. This vortex flow pushes building from side to side. Therefore, wind loads are more likely to cause resonance and cause the collapse of skyscrapers. What methods did engineers of the absolute world use to cope with wind loads? They adopted two ways to deal with the wind load problem. Let me tell you about building design to make wind-induced responses first. Based on the square model, we made a table about disposition and deformation proportions each building model has. The corner fillet building was less affected by wind loads than by square. Corner cut has a more unfavorable value than corner fillet model. 90-degree helical scale was less affected than the corner fillet. As twisted angle increases, the building was less affected by wind load. And it has more advantage if building is corner cutted. We were focused on corner cut model, helicoidal shaped model, and helical corner cut model. The helical corner cut shape has both the shape of the corner cut and the helicoidal shape. The helical corner cut shape could be approximation of absolute tower model in this way. Absolute tower has both an elliptical shape and a helical square rotated 209 degrees. Especially, absolute tower's twisted design has strength to wind load. One major advantage is a vortex control. Ordinarily square cylinder form makes intensive vortex when wind blows. Let me show you vortex created in square cylinder model. You can see strong vortex creation at the side of the building. And here's 180-degree helical square model. This is top view of wind state at helical building. For twisted square model, vortex are significantly different from that of square extrusion model. Twisted design is also effective to dispersing wind loads. We mark the movement of air when the helical square model affected wind. Wind flow near building surface, the air is dispersed, so it's more effective than other models. If the wind load affects the other way, movement of air is changed. So absolute tower secures stability to overturning moment by wind load and vortex resonance. Then let me tell you about the second method, shear wall structure. The wind load we are focusing on this week works in a horizontal direction on the building. Therefore, we need a wall to resist the horizontal direction of the building, and that will be shear wall. When the red and yellow arrows are wind loads in different directions, the wind loads work as above for one slab. There are two main ways to position the shear wall. First, placing the shear wall on the external wall of a building. Second one is placing the shear wall on the elevator and staircase walls, that means on the core of a building. Generally, shear walls are often placed on the exterior wall of buildings. In that case, the shear wall under the red line resists red wind load as shown above, and the shear wall under the yellow line resists yellow wind load as shown below. However, in the absolute world tower, there is no external wall, and there is a balcony outside the building. Therefore, it is not possible to arrange the shear wall on the external wall. But as mentioned last time, absolute tower is a flat plate structure, so load-bearing walls supporting vertical loads exist in the same location on every floor. If load-bearing wall is constructed with shear reinforcement concrete, we can use it as a shear wall that can resist vertical loads and horizontal loads at the same time. So in the case of the absolute world tower, the second method has been used, selecting elevator and staircase walls as shear walls. As shown in the figure, the dark blue part is the core shear wall surrounding the elevator and staircase, and rest are sub-shear walls. When I apply the above-mentioned method of operating wind loads to our building, the red walls operate as shear walls resisting wind loads in red direction, and the yellow walls operate as shear walls resisting wind loads in yellow direction. The overall operation looks like this. These fixed shear walls operate horizontally in each slab, acting like cantilevered beam anchored to the ground. This shear wall can resist 4 to 20 times bigger horizontal load compared to normal ramen structure without shear walls. These are references of this presentation. Thank you for watching our presentation.